Welcome to BKW Physics, and we're going to talk about polarization right now. Now, polarization is a word usually you might hear it when you're talking about cameras or lenses, and the definition, what it really means is that you align the waves so that they only exist in one plane. Now, before I even get into this picture, I want to talk about some examples. When you go fishing, and you're out in the boat or out on the water, and you look across the water surface, if it's a sunny day especially, you're going to get just a severe reflection off the water. And you're not going to be able to see down into the water, you're just going to see the sunlight reflecting off the surface, angle of incidence equal the angle of reflection, boom, it's going to hit you in the eyes, it's going to be bright, and you're going to be squinting all day long. Now if you put on some cheap sunglasses, it'll make that appear a little dimmer, a little darker, but you still won't be able to see into water. However, if you buy good polarizing sunglasses, when you stick those things on, boom, all of a sudden that glare disappears, and you literally can see down into the water, depending how clear the water is, but you no longer are blocked from seeing into the water by the glare. It eliminates glare. So that's kind of a visual, so you can kind of think of what's going on here when you have polarizing sunglasses. And we'll come back to that more when I show you a little demonstration. It'll make sense what's actually happening. But let's check this picture out. So if you have a light source here, it is incoherent light, which we talked about in our last lesson, meaning the waves are oriented all different ways. They're not in phase at all. And if you send it through a piece of polarizing film, which, by the way, really doesn't look like much. It looks like this one right here. This is a piece of polarizing film. It looks like something you'd make sunglasses out of, because you do. Okay, it's just a piece of plastic, and it looks dark. But on a much smaller scale, there are actually bars or lines in the polarizing material, so that when this incoherent light tries to pass through, it blocks everything except the one that lines up to the bars. So the waves that are like this can pass through, whereas the waves that are at all the other angles will hit the bars and they won't make it through the polarizing film. So now when you pass through on the other side, you have waves that are aligned in one plane. Now, you can use an analyzer, which, by the way, you know what an analyzer is? It's another piece of polarizing film. And if you take it and turn it the other way, so if we had it this way, and then we turned it this way, now the bars should block this light also, and what should you get on the far side? Absolutely nothing. So let's see if we can do that. That's a nice little demo. Let's see if we can make this happen in reality. So I'm going to bring out this old handy-dandy projector that I saved just for this purpose, because it doesn't really see any other use in the classroom anymore. So we turn on this handy-dandy projector, and you're going to smell dust start burning in a second. We're going to turn down the lights so that you can see we got some nice light here. Is that visible enough on the video? Yeah. All right. Now if I lay down one of these here, I'll erase this other stuff so you're not distracted by it. So all you notice is that it just got a little darker. No big deal. Okay, so that's your polarizer. I'm claiming, though, that all the light is lined up in one direction right now. Everything that passed through this film right here is now lined up in one direction. That's my claim. Here's my proof, because I need another one of these. Now see, it's the same exact thing. I just have two of the same thing. So if I overlap them this way, it gets slightly darker, right? But not really. It's like wearing two pairs of sunglasses. It just makes it a little bit darker. However, when I take this and I start turning it, so now the bars are starting to crisscross, I can prove to you, pretty much beyond a shadow of a doubt, that the bars are going this way, and the bars are going this way, and where they overlap each other, you can totally block the light. The light cannot pass through when the bars are at 90 degrees to one another. So you have polarized it and then analyzed it and proven that light can be aligned in one direction. Now, so we don't all choke out on this thing, I'm going to turn that off, get the lights back on here. Whew, that thing stinks. But back to the sunglasses. So you're out fishing. How can polarizing the light actually make it so there's no glare on the water? We'll back up a second. If there's glare, what is true about all the light that's bouncing off the surface of the water? It's all oriented how? Watch my hand. Like you got random light, it hits the surface. What is the part that bounces off? It's all in one plane, right? Everything that's coming off the water is in this plane. So if you wear your sunglasses so that the bars block that plane, what's it going to do? It's going to block all the light that came off the surface of the water because it was all in one plane. However, all the other light that's all kind of random, you still see. So it's not like all of a sudden you put glasses on and everything's black and you can't see. Those would be terrible glasses, okay? No, it just blocks the one that's all in one plane. So let's see if you understand. What if you're driving down the highway now and there's a truck that goes by you with a really shiny, chromed out, trailer on it, and the sunlight hits the side of the trailer and shines in your eyes, so you got this really bad glare. You're wearing your polarizing sunglasses, but they don't seem to do anything. Why?
That could be different.
Because it's different. I just told you the glasses are set up so that the glare like this will be blocked. So now the glare is coming like this. It's not going to block it. It's going to go right in. So how could you solve that? If it was really driving you crazy, what could you do? You take your sunglasses off and tip them sideways for a second, look through one eye or something like that. It'll block the glare. Okay? That's the solution. Now I know you understand that. So if we can spin to the back of the room, and Justin, come help me out here. If you can hold this in here, and Jeremy, you can hold this end down here. Don't let go, we don't want any accidents here. And actually, we don't have to stretch it too terribly far, but I'm going to have you guys kind of start. Why don't you just start sending some pulses and get a standing wave? Get a standing wave going here. Now, if I take these and I pretend this is the wave, the slinky or the snaky represents the wave, and these represent a polarizer. If I take this polarizer and I line up the bars so that they're up and down like this, I can get very close to this wave and it really has no effect. The wave goes right through. Can you see that? However, if I do this, I can basically, you keep making them. Go ahead and try. Okay? I can basically totally block the wave from continuing on. The wave will come up. It seems like it should be able to go through because I'm not squeezing it, notice. You know, I'm just putting the bars like that. But I basically can totally block the wave, or in other words, polarize it. So for today, polarization.